Hello everyone and welcome back. We have a couple of minutes before the start of class if anyone would like to ask me any questions. Hello Devin. So since it's Remembrance Day today, we will pause the class for about 1 minute at 11 a.m. Okay, so today I want to talk about something that comes up fairly quickly if you need to use probability in the work that you're doing. And that's this idea of infinite probability spaces. So to introduce those, we'll go back to the beginning when we defined this probability spaces, right? Remember there's a set S of outcomes and there's a probability function. And we said that S is a non-empty countable set. So non-empty is easy, it means it has at least one element. Countable though, you may or may not have seen the definition. It means that the set is finite, so there's just a finite number of elements in the set, or it's countably infinite. So that sounds a little bit circular since you say it's countable if it's countably infinite. Well, countably infinite has a very precise definition, and that definition is there exists a bijection between non-negative integers, and the elements of your set. So a countably infinite set has a bijection between its elements and the non-negative integers. And if you've studied these things, one of the surprises is there are some sets that are infinite but not countably infinite. So for us, we're interested in we're working on discrete probability here. We will run into infinite sets. They come up frequently, but they'll be countably infinite ones, meaning that there's a bijection between them and the integers. And for us, that means that if we want to list out the elements of the set, it's possible to do so in such a way that you'll write a list that for any element, it will eventually run into that element. In particular, if we want to sum up the probabilities of all the elements in the set, that makes sense because, well, we'll explain that in a second. So let's look at an example. So, really simple example, and if you've taken the data structures course with me or someone else, you run across this already, which is you toss a coin repeatedly until the first time it comes up heads. It's an easy experiment, right? You take a coin and you toss it. If it comes up heads, you stop immediately. If it comes up tails, well, you toss it again and repeat this way. So as long as the coin keeps coming up tails, you'll toss it again until the first time it comes up heads. So if you want to model this as a probability space, well, you get a set S that looks like this, right? It could be that your first coin toss is a head, so you get an element like this in S where your sequence of coin tosses only has one outcome, it's a head. Or the first one is a tail, but the second one is a head. Or the first two are tails, but the third one is a head. Or the first three are tails, but the fourth one is a head. Or, you know, the first four are tails and the fifth one is a head, and so on. And well, that's infinite for sure, and it's also countably infinite because, well, we can just think of, if you want a bijection between this and the non-negative integers, just say that each element here corresponds to the integer which counts the number of tails in the sequence, right? So this is element 0, element 1, element 2, element 3, element 4, and so on. So any outcome in here, there's exactly one integer that corresponds to that outcome. So that means that it is, well, that means it's 1 to 1 and on to. So it's a bijection. And just to get us used to this, we'll write this more concisely as the set of outcomes is a sequence of n or more, or n tails followed by a head, and n can be anything bigger than or equal to 0. Okay. So n is any integer bigger than or equal to 0. Then the outcomes that can occur in this experiment is 0 or more tails followed by that one head. And if we want to know what the probability function is, well, the probability of some particular outcome, t to the n h, well, we could do this with conditional probability, assuming that coin tosses are mutually independent, and if we do that, then we just get the products of these events. The first coin toss is a tail, the second coin toss is a tail, the third coin toss is a tail, all the way up to the nth coin toss is a tail, and then the n plus 1th coin toss is a head. Or you could do some fancier counting, but in this case, I mean, the answer is 1 over 2 to the n plus 1. Okay. All right, so that's the probability measure that we put on this probability space, because really the probability of this outcome, which consists of n plus 1 coin tosses, each of those coins has to come up exactly a certain way, and that happens each time with probability a half. All right. So if we go back to our definition of probability space here, we see that, well, we have an extra condition. So yeah, if I check this, I will see that this probability function is always bigger than or equal to 0, and it is also less than or equal to 1. Its maximum value is when n equals 0, in which case it's a half. So it satisfies this part, but to be a probability measure, it also has to sum up to 1. So if we sum all over the individual outcomes, then we should get 1. So we should check that just to make sure we haven't done anything weird. And so here we try and do that, and we say, okay, let's take the sum over omega in S, the probability of omega. Well, that's just equal to the sum as n goes from 0 to infinity of the probability of this thing, t to the n h, which is equal to the sum n equals 0 to infinity of 1 over 2 to the n plus 1. And let's make our lives a bit simpler. 1 over 2 to the n plus 1 is just 1/2 times 1 over 2 to the n. So that means we have a sum, and each of its terms is multiplied by a half, so we can bring the half out front. Okay, so you've probably seen such a sum before, and if you've taken a course with me and you've seen it, you've seen that there's a trick to show that this is equal to 1. It's related to the so-called Zeno's paradox. But let's be a little bit more careful here and do this properly. And the first thing we need to do is think about, well, what does this even mean? What is an infinite sum exactly? So it has a formal definition, and the definition is the following. If I want the sum n equals 0 to infinity of, let's say, something like x to the n, well, the definition of that, it's actually equal to the limit as let's say, yeah, it's equal to the limit as n goes to infinity of the sum little n equals 0 up to big N of x to the n. This is really the definition of an infinite sum. So when you see a sum that goes from something up to infinity, it really means it's the limit of finite sums, where you just keep taking the upper bound on the sum to be bigger and bigger and bigger. And so in particular, you may remember from calculus that limits don't always exist, right? Some functions don't have limits. And so that means that some infinite sums are not defined. So limits are not always defined, therefore the values of some infinite sums are not defined. And it's easy to cook up examples for instance, you know, the sum of minus 1, n goes from 0 to infinity of minus 1 to the n, that doesn't have a limit. It just keeps flip-flopping between 0 and 1. So let's try this. So let's try and evaluate this one, and this is a special case, right? So x to the n, we're considering here 1/2 to the n. So if we can solve this one, then we get an answer that involves x. We can substitute x with 1/2 and know the answer here. So in order to do that, we need to evaluate this thing. So here's the claim, is that the sum of n equals 0 to big N of x to the n is equal to 1 minus x to the big N plus 1 over 1 minus x. And that's true for any x which is not equal to 1. And why do I have to put in this little condition that x is not equal to 1? Well, if x equals 1, I have a problem, which is that I would be dividing by 0 in this expression, so that doesn't make sense. So let's not do that. So how do you prove that? Well, this thing on the left here is just x to the 0 plus x to the 1 plus x to the 2 plus x to the 3 plus x to the n. That's this thing on the left. And this thing is claiming that this is equal to, sorry, not x to the n, x to the n. And that's claiming that this is equal to 1 minus x to the n plus 1 over 1 minus x. And, well, proving this is the same thing as if I multiply both sides by 1 minus x, then I get this, right? So this claim here is equivalent to this claim here, that I multiply both sides by, if I multiply both sides of this by 1 minus x, I get this expression that says 1 minus x times this big sum is equal to 1 minus x to the n plus 1. And actually now it's easy because I can do this multiplication. And if I do this multiplication, well, first I have to take each term here and multiply it by 1. So when I multiply by 1, I just get the same thing. And now I have to take each term and multiply it by minus x. So then I get a minus x times x to the 0 is x to the 1. X times x to the 1 is x to the 2. X times x to the 2 is x to the 3. And so on. Here I have a x to the n minus 1, which when I multiply it by minus x becomes a minus x to the n, and then finally minus x times x to the n is a minus x to the n plus 1. And now you see everything cancels out. So these cancel out, these cancel out, these cancel out, everything in here cancels out, including these, and all we are left with is x to the 0 minus x to the n plus 1. Well, what's x to the 0? Anything to the 0 is 1. So this is 1 minus x to the n plus 1. And so indeed, this thing on the left-hand side is equal to this thing. Okay. which is this equivalent to saying that this sum is equal to this. All right, so that proves that claim. So now we understand the finite sum here. And all we have a closed form for it, which is this. And now we just need to take the limit of this thing take the limit as it goes to infinity. So let's do that. This sum is equal to this, so that means that the limit as n goes to infinity of this sum is just equal to all right, so it doesn't totally solve it because we've still got this x to the big N here. And I want some simple form. And well, if I look at what I'm interested in using this when x is a half. Later we'll want to use it for something like x equals 3/4. But basically when x is a probability, essentially, is when we want to use this thing, which means it's between 0 and 1. And if x is between 0 and 1, and in particular, if x is smaller than 1, then, so limit as n goes to infinity of x to the n plus 1, that is equal to 0 if, in fact, as long as x is bigger than minus 1 and smaller than 1. So if the absolute value of x is smaller than 1, then as I keep raising it to a higher and higher power, the absolute value gets closer and closer to 0, which means in the limit it's equal to 0. So this thing just disappears, and we get 1 over 1 minus x, and that's only true for x between minus 1 and 1, not inclusive. I hardly in my work have I ever used negative x's in here, but it's nice to know that you could put negative x's there. For us, x is usually a probability, so it's between 0 and 1, so we're good there. All right, good. So I'll get rid of the proof of this and just leave up the result. And now if I take x equals a half, 1 over 1 minus x is 1 over 1 minus 1/2 is a half, is 2. And that means this sum here evaluates to 2, so I get a half times 2 is equal to 1. Okay, so there's a careful check that this thing really is a good probability function for this particular set of outcomes. It satisfies everything. The values are between 0 and 1, and they add up to 1. And just for your own reference, you see that in this course, I think it's explicitly mentioned in a few places that this course is about discrete probability. And the discrete here refers to the fact that we only consider these kinds of probability spaces where S is countable. If S is not countable, then things stop making sense here. In particular, this sum doesn't make sense. And if you want to work in that kind of setting, then you have to stop working with sums and start working with integrals. But we don't have to do that here, so we're good. Okay, so let's look at another example. And it's an example called Who Flips the First Head? Okay, and it's a game, and the game is played as follows. There's two players, player 1 and player 2, me and you, and they take turns tossing a coin. Player 1 goes first, and then player 2 goes, and then it goes back to player 1, and then player 2 goes. So it goes back and forth like this. And the game ends when the first player tosses a head, and that player is the winner. Okay. So the winner is the player who tosses the first head, and player 1 goes first. All right. So, I show up and I say, okay, I'm willing to play this game for money. Whoever wins, we'll bet, I don't know, $1,000 on this game, and whoever wins gets the $1,000 from the loser. Do you want to go first, or do you want to be player 1, or do you want to be player 2? So you think about it for a little bit, and you think, well, would I rather be player 1 in this game or player 2? Who has the advantage? So what's the question is, what's the probability that player 1 wins? Okay. And if you think about it for a few seconds, you'll realize that player 1 must have the advantage. And here's why. Player 1 tosses the first coin. That first coin toss comes up heads with probability 1/2. So that means the probability that and if that happens, player 1 wins. He tossed the first head, the game's over, player 2 doesn't even get to go. And if that happens, that player 1 wins, so that means that the probability that player 1 wins is at least 1/2. Well, since there's only two outcomes, player 1 or player 2 wins, that means the probability that player 2 wins is at most 1/2. But without thinking any more about it at all, you realize that if the game is biased at all in favor of someone, it's biased in favor of player 1. And if you think about it a little bit more, you'll realize, oh, actually there's another way player 1 can win, and that's if he tosses tails, player 2 tosses tails, and also tosses tails, and then player 1 tosses heads on his second toss, right, when the coin comes back to him. And then add that in, and you'll realize, okay, his probability that he wins is actually bigger than 1/2. So player 1 is definitely has a better than 50% chance of winning. So I would choose to be player 1. And now you want to think a bit more and think, okay, what is the probability that player 1 wins? Because maybe I come into this room and say, yeah, we're going to play this game, and I'll say, I'll be player 1. So I declare I'm going to be player 1, but if you win, I'll give you $2,000. If I win, you have to give me $1,000. And then you want to know, okay, is that a fair game? It seems like you have a chance to win 2,000 and only have a chance to lose 1,000. But to know whether that's a good idea or not, you need to know what the actual probability is of you winning versus player 1 winning. So let's work it out. So conveniently, the probability space is the same one we've just been discussing. It's a sequence of coin tosses that starts with n tails, 0 or more tails, followed by a head. Okay. Now, the coin is going from one, first player 1 does the first one, and then player 2 does the second one, and so on. So it's going back and forth, but still there's just a sequence of coin tosses that determines the result of the game, and the game is over the first time somebody wins a head. And so let's define the event A is player 1 wins the game. Okay. And we already sort of started to work it out. This event A looks like the following. Player 1 tosses heads immediately and wins, or player 1 tosses tails, player 2 tosses tails, and then player 1 tosses heads the second time they get the coin. Or player 1 does tails, player 2 does tails, player 1 does tails again, player 2 does tails again, and then finally the coin is back in the hands of player 1, and they toss a head, and so on, which this is kind of ambiguous what this means, so let's write it out using the same notation we used here. This is the set t to the 2n h, where n is bigger than or equal to 0. Okay. So what happens is there's an even number of coin tosses, and then player 1 tosses heads. That's how he wins. Right? Those are exactly the outcomes in which he wins. There could be 0 coin tosses and player 1 tosses heads, or there could be 2 coin tosses and then player 1 tosses heads, or 4 or 6 or 8 and so on. So the total number of coin tosses is odd, but the first, all but the last one are tails, which means that it comes back into the hands of player 1. Okay, so that's the set A that defines the event player 1 wins the game, and we want to know what's the probability of A. Well, just remember the definition is you sum over all the events in A of the probability of that event. And for us, this tells us the events. So there's some number n, 2n of coin tosses, all of which come up tails, and then the heads. So we're looking at the probability of T2N H. It's that thing. So what is the probability of T2N H? That's just the sum n equals 0 to infinity. So now we're doing 2n tails instead of just n. So that's going to be applying this formula, but substituting n with 2n, we get to the 1/2 to the 2n plus 1. This plus 1 is annoying, so like before, we bring it out front. Okay, we have this thing for dealing with sums of x to the n that we saw already, but now we have this. Another way to write this is 1/2 to the 2n. So that doesn't look like it's in this form, but if you remember, if I have a to the b times c like this, that's the same thing as a to the b to the power c. So exponentiation distributes in this way. And so for us, our a is 1/2, our b is 2, and our c is n. So that means we can write this like 1/2 squared to the n, which 1/2 squared is just 1/4. So that's 1/4 to the n. And now we have this thing. So now we apply this with x equals 1/4, and we learn that it's equal to this. So let's be careful. 1/2, applying that up there with x is 1/4, we get 1 minus 1/4, which is 1/2 times 1 minus 1/4 is 3/4. But we have 1 over that, so it's actually 4/3. And so we get, in the end, 2/3. 4 divided by 2 is 2, giving us 2/3. So the probability that player 1 wins the game is 2/3. And that means the probability of not A, which is the event player 2 wins the game. So player 1 doesn't win the game, player 2 wins the game, by the complement rule is 1 minus the probability of A, which is 1 minus 2/3, which is 1/3. So if someone comes into a room and offers to play this game for you, with you, and says, okay, well, I'll be player 1, you get my $2,000 if you win, and I get your $1,000 if I win, then whether you play the game or not depends really on whether you're feeling lucky or not. Yes, the person is offering you, the prize money is twice as much as the loss money. On the other hand, the probability that you lose, which is this, if you're the second player, this is the probability you lose, it's twice as much as the probability that you win. So in the end, it's kind of a draw. In fact, when we learn about expected values, you'd see that if you played that game, your expected winning is 0. Okay. All right. So that's an example that it takes a little bit of work to analyze, but right away our intuition was hopefully spot on. Well, so the question is, it's a fair game. Whether or not it's a fair game depends on the bets. So if you're doing this with 2-to-1 odds, then it's sort of 2-to-1 odds in, well, in favor of the first player. I guess that's how they express this in gambling. Then it's a fair game. So the odds are 2-to-1. Meaning that if you're the second player, you better get twice as much money if you win than if you lose. Yeah, so in our intuition, you didn't have to think too hard about this to realize that player 1 has the advantage, and with a little little bit of work, you can figure out exactly how big that advantage is. He's twice as likely to win. Let's play another game. And this is a variant of this. This was too easy, and it was too obvious that player one has an advantage. So let's look at who flips the second head. So now the rules of the game are exactly the same, except that the first time the coin comes up heads, we keep going, alternating back and forth. And the next time it comes up heads, so the second time overall that it comes up heads, whoever tossed that heads is the winner. Okay. So now things change very much, because this isn't the possible outcomes of this game, right? Now we need to have outcomes that have two heads in them, exactly two heads. The game is over when the second head happens. So we'll figure that out, but spend the next minute or so trying to decide now. In this game, this modified game, whoever wins, the person who flips the second head wins. Who has the advantage, player one or player two? And feel free to blurt out your guesses in the chat window. Okay, so there's some guesses here. Some say player two has the advantage, so those were the first ones, actually most of them. Others say player one. Maybe it's fair, maybe now the odds are 50-50. One useful observation is that, of course, the argument we used before totally disappears, because player one does not win on their first flip, no matter what. And so we don't have any sort of obvious rule like that. On the other hand, player two can win on their first flip. Right? Player one flips heads, and then player two flips a head. They win, but the probability of that is only a quarter, so that doesn't already put player two necessarily at an advantage. So to know the answer, we're going to have to work it out, and there's a couple of ways to work it out. We'll do first the hard way, and then the easy way. All right, so this is now the outcome space. There's some number bigger than or equal to 0 of tails, then somebody flips the first head, then there's some number bigger than or equal to 0 of tails, and somebody flips the second head, then the game is over. Okay. So that's this thing. M and N can be any integers bigger than or equal to 0. And the probability of any particular outcome, well, this is just a very specific sequence of n plus m plus 2 coin tosses. So the probability that we get exactly that sequence is 1/2 to the n plus m plus 2. So that part's easy. And now let's look at the event A, as before, is player 1 wins the game. Now, what does that look like? Well, it's a bunch of events that look like this. T to the n heads, T to the m heads. And what has to happen is that m plus n is odd. Let's think about that for a second. If m plus n is 0, that means no tails were flipped and it's just 2 heads. Player 2 is the one who tossed that second head. If m plus n is 2, that means that there were 3 coin tosses. So that if m plus n is odd, sorry, why did I say odd? Yeah, sorry. If m plus n is odd, then that means that m plus n plus 1, which is the number of coin tosses before the winner, that thing is even, right? If m plus n is odd, then you add 1, you get an even number. And after an even number of coin tosses, the coin is back in player 1's hand, and he makes that final coin toss. So this is the way that these are exactly the outcomes where player 1 tosses that final winning coin. Okay. All right. So now let's break it up into two different events, which are A1 and A1 you can think of as P1, player 1 tosses the first and second head, and the other possibility is that P2 tosses the first head and P1 tosses the second. Okay. Then of course A is just the union of A1 and A2, right? So if player 1 wins, he tosses the second head, and then you just split that up into 2 disjoint subsets, where one of the sets counts the outcomes where player 1 tossed the first head, and the other one counts the outcomes where player 2 tossed the first head. So A is equal to A1 union A2. These things are disjoint, and therefore the sum rule tells us that the probability of A is equal to the probability of A1 plus the probability of A2. Okay. So let's try and figure out probability of A1. So A1 we can write this like t to the n h t to the m h, and you need that. In this case, if player 1 tosses the first head, that means that n is even, and if player 1 tosses the second head, that means that m plus n is odd. And if n is even, but m plus n is odd, that means that m is odd, right? An even number plus, well, only an even number plus an odd number can make an odd number. So saying this is exactly the same thing as saying n is even and m is odd. All right, and maybe because eventually we're going to want to write down a sum, we should, instead of even and odd here, let's put in, let's express this in terms of things we can sum cleanly. So that's going to be same thing, t to the n h, t to the m h, and here this will be n. Is supposed to be even, so let's call that 2k, and, or, let's write this another way. T to the 2k and t to the 2l plus 1, such that k and l are bigger than or equal to 0. So if I take k to be all integers bigger than or equal to 0, then 2k goes over all the even integers. And if I take L to be all the integers bigger than or equal to 0, then 2L plus 1 goes over all the odd integers, right? 2L goes over all the even integers, and then add 1 gives you the corresponding odd integer. Good. So that's a good description of the set A1 that we can work with. And so now we can sum. So probability of A1 is the sum. It's a double sum now. We have a k running from 0 to infinity. Inside of that, we have an L running from 0 to infinity of the probability of this thing, t to the 2k, h, t to the 2l plus 1, h, so what's the probability of one of these things? How many coin tosses are there? I count 2k plus 2l plus 1 plus 2 plus 3. Okay. So now that's the probability of this thing. Let's get rid of the annoying stuff. This plus 3 is annoying, but that just means we have this enormous double sum, and every term in that double sum is multiplied by 1/2 to the third, or 1 over 8. So let's just bring that out front. Now, so if you're not used to working with sums that much, this may seem scary, this double sum. If you're better at programming, it's easier to think of this in terms of two for loops. There's an outer for loop. That's the loop that runs over all the values of k, and there's an inner for loop that's the loop that runs through all the values of L. And if I just focus on this inner loop, so this inner sum, then that whole sum happens with a fixed value of k, right? So if I hide this outer thing, then what I see is there's a variable L that keeps changing, but the variable k does not change. So inside that sum, it's basically a whole bunch of terms. Each one of them is multiplied by 1/2 to the 2k. So I can do the same thing and pull that out front. So I still have my 1/2 out front. Then I have this sum, k equals 0 to infinity. And there's this 1/2 to the 2k. And that multiplies the sum L equals 0 to infinity of 1/2 to the 2L. All right, good. Now, if you have a photographic memory and excellent recall, you might realize we have seen this one before. So this innermost sum here, this is the sum of 1/2 to the 2L. L is going from 0 to infinity. We saw that that is actually the sum of 1/4 to the L, where L goes from 0 to infinity. And we plug in x equals 1/4. So that means it's this sum with x equals 1/4. And we get 4/3. We get 1/3/4, which is 4/3. So let's put that in. So we have a 1/2. Still haven't dealt with this sum on the outside. But this sum on the inside is just 4/3. And, well, again, now we have a sum where everything in that, each term is multiplied by 4/3, so we can bring that out front. So this 1/2 becomes that. So 4/3 times 2 cubed. That, what's 2 cubed is 8. 4/8 is 1/2. And we will spend the next minute or so having a moment of silence. So I'll give us about 2 minutes that accounts for the time delay. Okay. So, yeah, so we're still beating up this sum. So what do we get? This is 4 over 8, which is 1/2. So that gives us 1 over 6. And now look at this sum. We've seen it before as well. It's the same one we just did. It's equal to 4/3. So we get 1 over 6 times 4/3, which is 2 over 9. All right. So the probability of A1 works out to be 2 over 9. What was A1 again? Well, A1 is the probability that player 1 wins by tossing both the first and the second head. We also need to know the probability of A2, and we can do that. So we follow the same kind of reasoning. The only difference here is for A2, that means player 2 tosses the first head. So that means the leading sequence of, let me just write this down. So we get k is 0 to infinity. L is 0 to infinity of the probability of tails, 2k plus 1, heads, tails, 2L, heads. Right. So A2 is the event that player 2 tosses the first head and player 1 tosses the second head. So that means before the first head there was an odd number of coin tosses. Then player 2 had it and tossed that first head, and then there had to be an even number of coin tosses so that it comes back in the hands of player 1, who tosses it and gets the second head. And actually, look what happens here. The probability of this thing is exactly the same as the probability of this thing, right? Here we have a 2k and a 2l plus 1. Here we have a 2k plus 1 and a 2l. But all that matters is the length of this thing, which is 2k plus 2l plus 3. So that's just going to be equal to this double sum. K equals 0 to infinity. L equals 0 to infinity of 1/2 to the 2k plus 2l plus 3. And we don't need to do that again because we beat it up already and we saw that that's equal to 2/9. That's exactly what we did here. Okay, and then we finish. So that means that probability of A is 2/9 plus 2/9 is 4 out of 9, which is less than 1/2. So for those of you who guessed player 2 has the advantage, you were right, because the probability that player 1 wins is only 4 out of 9, and 1/2 is 4.5 out of 9, so probability that player 1 wins is less than 1/2. So player 1 is at a disadvantage. Player 2 has the advantage in this case, and now you know exactly how much the advantage is. It's not quite as bad as it's not quite as lopsided as the first game. In the first game, the second player had, the first player had twice as much, his probability of winning was twice as big as the second player's. here the second player has an advantage where his probability is 5/4 the probability of the first player. So not anywhere close to 2. All right. So that's the answer. And if you, you know, sat through that, then you, well, you're probably asleep by now or gone. But you might think maybe there's an easier way to get that answer. And this happens a lot, where you see the answer and then, you know, you struggle and you finally get it, and then think some more and think why. Maybe after seeing it, it gives you some clue. In this case, 4/9 is not very informative, but maybe there's another way to see it. And it turns out that there is. So I'll erase this derivation now because you can always just rewind if you want to look at it again. And the easier way to get this is to think, well, maybe to apply some intuition. So there's this law of total probability that we kind of mentioned. It's called a law rather than a theorem or a lemma, because it's too obvious to be a theorem or a lemma. It was really just the definitions that tell you, right? So it says that if I have some events A and B, the only condition is that the probability of B should not be equal to 0. Then the probability of A is just the probability of B times the probability of A given B. So plus the probability of not B times the probability of A given not B. Okay. So you think of it this way. If A can happen in one of two ways. Either B happens with this probability, in which case we're living in a world where we know B happened, we want to know the probability that A happened given that B happened. Or B didn't happen, in which case we want to know if A happened. Well, we know we're living in an outcome in which B didn't happen, so we want to know the probability of A given not B. And if you try and write a proof of this, well, all you have to do is expand the definition of probability of A given B, and you realize that all you're left with in the end is the probability of A intersect B plus the probability of A intersect not B. Those are two disjoint events, and so the sum rule says that the probability of that they contain all of A, so the sum rule says that those things are equal to the probability of A. So nothing exciting there. That's why it's a law. If someone tells you something is a law, in mathematics it means it's just trivial. And in other disciplines, like, I don't know, physics is one. If someone tells you a law, it's something that they assume is true, but probably it's not true. It's just a good approximation for reality. But in mathematics, if someone tells you a law, it means it's true, and it's not even worth writing a proof down. Okay, so that's the law of total probability. How could we use it here? So let's go back to game 1. Who tosses the first head? Okay, that was game 1. And then we have game 2. Who tosses the second head? Okay. And now, when we play game 2, we keep playing until we see a second head. And so that really means, actually, before that happens, we've fully played game 1, right? We basically are playing game 1 until somebody wins game 1, and then we continue playing game 2. Now the only difference is, depending on who won game 1, that determines who starts first in game 2, right? So if player 1 tosses the first head, that means after that, so player 1 tossed the first head, now player 2 is starting, and they're going to win if they toss the first head, the next head. But that means what's really happening after player 1 tosses the first head, we're starting another version of game 1, except player 2 is going first. Okay. So we can say, let X be the event, player 1, or I don't know, let's say B actually, so that it looks like this. B is the event, player 1 wins game 1. Okay. A is still going to be the event, player 1 wins game 2. And so we're going to use this. All right. So B here is the event that player 1 wins game 1. And another way to write that is to say that player 2 starts the second round. Okay. So, the picture looks like this. So this is round 1, everything up to the first head, and this is round 2, everything after the first head and up to the next head. And notice round 2 looks just like the first game, right? You keep tossing coins until you get the first head. Okay. So So B is really, player 1 wins the first game, so that means here, player 1 won, they toss that head, and now we start round 2, except player 2 is the starting player in round 2. And we know that the starting player has probability 2/3 of winning this game. So, probability that player 1 wins round 1, so let me even write that this way, wins round 1, that's the same thing as player 2 starts round 2. Okay. So, what's this probability that player 1 wins round 1? Well, that's the first thing we studied. That was 2/3. What's the probability player 1 wins? In this case, means wins round 2, given that player 2 is the starting player in round 2. That's not so good. That's not 2/3. That's only 1/3, right? If player 2 is the starting player, then the probability that player 2 wins that second round is 2/3. And so that means the probability that player 1 wins the second round is only 1/3. So we get 2/3 times 1/3 for this part. And now what about this part? Well, not B is the event that player 2 wins the first round, which happens with probability only 1/3. And the probability of A given not B is is what happens. So given not B means at this point, so the picture would look like this. Round 1 ends, player 2 just tossed that head, and now player 1 is starting round 2. That's the original game we studied. Player 1 starts first, and you go until the first coin toss, and that means that player 1 wins with probability 2/3. And that's just 2/9 plus 2/9 is 4/9. So that's the almost calculation-free way to get the same result, and that's by thinking about the game as being played in rounds. There's a round 1 and a round 2. Winning the first round may or may not help you. In fact, winning the first round of this game is not good for you. If you win the first round, then you're probably going to lose the whole game. But breaking it up this way into those two events based on who wins the first round, who wins the second round, gives you an easy proof. And some of that proof, also showed up when we did the calculations. In fact, the events B and not B, they correspond to this event, player 1 tosses the first head, or the event player 2 tosses the first head. So it's really doing the same thing, just one way ends up being involving more calculations, and the other one involves sort of a step back and looking at the whole game. And as an exercise, you guys can think about, okay, what about the general version of this game? So the first version, who tosses the first head, is really unfair. The second version, who tosses the second head, is a little bit more fair. What about who tosses the third head, who tosses the fourth head, who tosses the 50th head? Are those games only getting more and more fair, or are they getting further and less and less fair? And if you want to tackle that, don't do a sum. Don't do it with a sum that involves 50 nested sums. Think of it this way, and think of using induction. Solve it first for solve the game. Who tosses the k-1th head, and then figure out the probability of the game. Who tosses the kth head? You'll get a solution that way. Okay, so it's a good guess. So that's it for today. If you have any questions, I can answer them now. yes, I can answer that question. So the question is, when we only have one head, the probability of getting head should be exactly 1, but here it would be 1/2. Can you explain this, please? No, I mean, in the first example we did today was just considering the experiment of tossing a coin until the first time it comes up heads. So forgetting about the game. And there we saw that the probabilities of, so the outcomes are just a head, or a tail and a head, or a tail and a tail and a head, or 3 tails and a head, or 4 tails and a head, and so on. And the probabilities of those events, the probability of getting just a head is 1/2. The probability of getting a tail and a head is 1/4. The probability of getting a tail and a head is 1/8. And so we were just adding up the probabilities there to make sure that indeed they add up to 1. So you get this sum 1/2 plus 1/4 plus 1/8 plus 1/16. And indeed that does add up to 1. So that just means that another way to think of that is if you toss a coin long enough, you will eventually get a first head. Right? So if you keep tossing, you eventually get a first head, but there's no guarantee at all on the number of coin tosses you will have to do to get that. In particular, for any value n, there is a non-zero probability that you'll have to toss the coin n times before seeing that first head. I hope that answers your question, or I hope I understood that question. Any further questions? Okay. So thanks for showing up again today. It's always helpful to have an audience. And I will see you either this afternoon or on Monday.